Welcome everybody to Minnesota Robotics Institute's spring webinar. We're so glad that all of everyone could make it as well. We got a whole host of research presentations as well as a presentation from the director of MnRI, Nikos, who's going to speak a little bit about the Institute's and the MS program. Hi, I'm Ray Wyson. I do marketing and communications for the College of Science and Engineering, as well as, of course, the Minnesota Robotics Institute. We have joining us Brad Holschuh, who is from the College of Design, Derya Aksaray, who is from the Department of Aerospace Engineering and Mechanics, and then Catherine Qi Zhao will be popping in just a little bit. She's running just a little bit late for her presentation. She's from the Department of Computer Science and Engineering. So I'm glad we got sort of a whole wide array from across the college and even outside of the College of Science and Engineering as well. So we are stationed right in the middle of the East Bank campus at the University of Minnesota, right in the middle of the College of Science and Engineering. As you can see from the map, we are sort of in the middle of all of the departments, which is kind of the theme of MnRI and robotics in general as well. We are stationed in Shepherd Laboratories, the first two floors of which just recently received about $12 million renovation. It's an amazing space. We have full-scale robotics laboratories. We have grad offices, faculty offices, conference rooms. The solar vehicle lab is in the building. They have full room to bring their solar vehicle car in and out. It's an undergrad program, and we're always happy to have them in the building. We have a two-story drone lab in which I'm sure a lot of aerospace, Derya in particular, maybe utilizes where they can test drone and fly some stuff indoors when the weather is not so formidable. And much more. We got a great space. So I think with that, I'm going to relinquish screen share to Nikos, who's going to sort of give an overview of the center as well as the MX program. Like I said before, Nikos, feel free to share and.
Thank you. So good afternoon, everyone. I'm Nikos Papanikoloupoulous. I'm the director, and also I will try to cover a few of the topics regarding MnRI and also our master's program. Just give me 1 minute so I can. So why robotics and why basically robotics in Minnesota? If you see, we are facing a new reality. We have robots in warehousing, in supply chain. In fact, if you see the investment that different entities like Amazon and UPS are placing into robots, it's just unbelievable. We have surgical robotics with Da Vinci, but we have also Medtronic investing heavily. We have the Google car. We have all this activity about autonomous vehicles. And if you look at the numbers are staggering. For example, the projection is that the robotics market worldwide in 2025 is going to be $500 billion. If you look at companies that really were disruptive in this whole robotics enterprise, iRobot has sales of hundreds of millions of dollars, the capitalization that exceeds $2 billion. And if you look at the outreach, robotics is one of the most effective ways of reaching all these kids and promoting science and engineering. And Minnesota has the most first robotics teams per capita than any other state in the nation. So I want to show you a few video clips. This comes from Amazon. And we're going to see all sorts of mobile robots, manipulators. So the orange ones are basically kivas that became Amazon Robotics, which are used in order to move goods. And these do not only need to interface with other robots, but also they need to interface with humans. Especially in busy periods, one of the biggest problems is actually how one may interact, how the human workers may interact with these mobile platforms that you see here. Now, everybody can understand the implications of robotics, or the implications are fairly obvious when we see all these problems in supply chain. And think also about automation and robotics being part of autonomous trucks that are going to, because we have a tremendous shortage of truck drivers. And what robotics technology may offer on that domain as well. Another aspect that's very interesting and is not clear from this video is actually the use of robotics in order to augment the capabilities of the human worker, like exoskeleton devices that the worker can move in order to be able to lift weights. Here you are going to see something that is little known, but Amazon warehousing is one of the heavier users of all these monsters, manipulators that move whole pallets. And you can see, if you visit the facility, the Amazon facility in Chanhassen, you can see some of these robots in operation. And these are used more heavily in 24 hours than the Kiva robots. The Kiva robots, still there are issues of integration, interaction with humans, and so on and so forth. So I'm going to stop here and move to So if you look at some gaps, and this is a few of the reasons that drove us to create the Robotics Institute, there is a lack of proper training that blends robotics with other disciplines, for example, design, ethical issues, engineering, real-time programming. And we need a more holistic approach to the curriculum that is going to provide the proper background. There are concerns about data privacy and a loss of jobs. And in fact, whenever they are asking me about this, I mentioned the example of Rotolabs, which took an industry that it was lost in Minnesota, and now they employ more than 2,000 employees. There is injection molding, but injection molding the digital age plus 3D printing, and is one of the companies where the presence of UMN alumni is very significant. And I mentioned this as an example of additional jobs that we can create by effective use of robotics and automation. We need to rethink and redesign planning, control, sensing, and actuation with an emphasis of producing real-world robotic systems. We are missing benchmarks. We don't know exactly what works well in real-world settings. So we need to have, like computer vision, we need to have these benchmarks. And in fact, the biggest challenge is actually the ability to attract and retain high-quality faculty and students to academia. When industry is so aggressive, it's not only going to attract faculty, but also students. And this is one of the characteristics of the last 5 years. We have very few students who receive a PhD in robotics and follow an academic career. The MnRI key areas, MnRI started basically by the state as part of the MnRI facility with $4 million as a line item. Of course, we are not getting the $4 million. Then Jim Weinel's generous donation of $10 million plus additional matching from the university gave us the ability to have this marvelous space. And we're in the process of negotiating more many more significant gifts from donors and industry. Key areas are cognition, perception, robot control, and robotics hardware. And we're very much interested in 3 areas: applications in agriculture, medicine, and autonomous vehicles. And also we're interested in outreach and commercialization. Several of us are involved or have started companies. For example, one company that was at the beginning of the robotics effort in the Twin Cities is the Robotics, that is one of the largest, or used to be one of the largest builders of defense-related robotics. Basically, robots that used to deal with improvised explosive devices. Some of the work that is happening at MnRI and the students of MnRI, who are actually not only the master students, but the PhD students, I will show you the work of Ruben Desa on a transformer UAV. And you can see a UAV that starts as a quadrorotor. Ruben moved, he was with us as a freshman, then moved to OpenAI, and now moved to another startup in the Silicon Valley. And you can see how the device was transformed into a fixed wing state. Another transformation to a quadrorotor. And you can see the screams, and you can see Ruben celebrating. So I'm going to spend a couple of minutes about some of the student stories. I mentioned Ruben got his, again, robotics multidisciplinary. He got his PhD in mechanical engineering. We have, for example, Luis Guzman, who is now at Amazon Go. He got his master's in robotics from us last December. He was a MnRI scholar, and it was a great. We are very fortunate to have a great set of kids. My view of robotics is that robotics is all this very cool hardware, but even if we forget this hardware, what remains is actually sensing and data. We are looking at more and more advancements coming in data-centric systems, especially if you look in medicine or in agriculture. The new directions is actually we need to take the data as part of our mission, part of basically the training that we provide. And we want roboticists that can harvest, process, analyze data, and extract useful insights. And there is no current training for roboticists that brings together skills such as machine learning, statistics, cloud computing, and visualization. Let's talk, let me say a few words about the master in robotics. Currently, we have 65 students minus 5 who graduated early this fall, so 60 students. We plan to accept to have another cohort of around 35 to 40 students. This is 31 credits course, which is heavily focused on research, either with a Plan A master thesis or a Plan B capstone project. The elective courses, the main courses are provided by all sorts of departments ranging from design, housing and apparel to aerospace engineering, computer science, electrical, mechanical, biomedical, statistics, math. We have 65 faculty involved to some degree. And another characteristics is actually we have very high retention rate. All these years, we lost only 2 students for reasons that didn't necessarily have to do with the institute or the efforts. More than 50% are directly supported by MnRI or teaching assistances or research positions. And in fact, as I'm interviewing new admits, it is very difficult to convince them because the majority of the other master programs, almost all of them, do not offer any financial support. But we're very fortunate that we have the MnRI support in order to support these kids in their education. It's very important to mention the connections to industry. For example, we have partners like Honeywell who have people like Honeywell MnRI fellows who are once a week inside the building. We have companies like Histosonics and Cetera that have 5 or 6 of our current students or graduates in their staff. And our list of partners involve even state agencies like the Minnesota Department of Transportation, who used to employ one of our current students. Now, let me tell you a little bit of the story of Luis, who came as a math bachelor's from University of Wisconsin. And he built in 4 months this interesting simulation in Gazebo in order to test the ability of the feasibility of someone monitoring human gestures, and then teach a Kinova robot that you see on the right in order to execute different movements in space. So this resulted in a paper, in an upcoming paper in the Robotics and Automation Letters. And again, this was just in 3 months and part of his capstone project. So I'm going to stop here, and I would like to thank Brad, Derya, and Catherine for giving you their perspective on robotics and their work. And without further ado, Ray, should we take questions now, or we should leave it at the end?
We're going to wait till the very end to take questions. Again, I put this in chat, but if anybody has a question, feel free to write it down in the chat, and we'll do our best to address it. Derya, I believe you are up next. Feel free to share your screen and start whenever.
Sure. Okay, everybody sees my slides in the regular presentation mode, right?
Looks great.
Okay, great. So hi, everyone. I'm Derya Aksaray. I'm an assistant professor in the Department of Aerospace Engineering and Mechanics. And today I'm going to talk about some of our recent work on reinforcement learning with complex objectives and constraints. So reinforcement learning is a very popular area under machine learning, and the goal is discovering an optimal behavior through trial and error interactions with the environment. And if you just Google reinforcement learning, you will see this very popular picture where we have an agent, which is our decision maker, and the decision maker makes some actions, and then the environment reacts to that with some next state and rewards. And by observing these rewards, it tries different actions, and ultimately it learns the optimal behavior. And reinforcement learning has been used in many domains, for example, for motion planning problems, or learning some skills like grasping, walking, or even learning some strategies in games. And the key thing in reinforcement learning is the designer of the task provides feedback in terms of a scalar function. And what I mean by that is, let's say we have a drone, and the drone is supposed to monitor the yellow region as long as possible, and it has to avoid the red region. So as the task designer, we can give a very positive reward to the yellow region and a negative reward to the red region, so that and all the other regions can be 0 reward, So when the drone, for example, visits a state in the yellow region, it will receive a positive reinforcement, meaning that in the future, it will tend to take actions that will take it to the yellow region. And the same thing for the red region. If it's a negative reward, it would be a negative reinforcement to the system. So in the future, it will avoid taking actions that will take it to the state in the red region. So by trying different actions in this space, it can actually learn the optimal plan, which would be flying over the yellow region as long as possible and avoiding the red region. Now, in our research, we are motivated by tasks that could be more complex than the example that I showed. For example, what I mean by complex task is, let's say we have our robot, and again, it's going to explore its environment, but the task is first go to A and then go to B. So there is some ordering between the regions. So similar to the previous example, in order to make region A desirable, we can give a high reward, a positive reward to region A and a negative reward to region B, so that we can make sure that the robot first learns how to go to region A. But whenever region A is visited, then we have to make changes in the reward function. So this time region B should have a positive reward so that it becomes more desirable. So as you see, in the face of these complex tasks, we would need some time varying rewards. And it's not very clear how to encode reward functions that is going to ensure the learning of complex tasks. So that is one problem that we are trying to address in our research project. And the second thing is the constraints during the learning. For example, in the same problem, suppose that while the robot explores the environment and learns, for example, the positive reward areas, let's say it has a constraint like periodically visit this yellow region during the learning process. For example, this could be a recharging station or a location for data upload, and periodically we may want the robot to visit that location. In the standard methods, such constraints are not enforced throughout the learning. For example, if you don't periodically visit region C, the agent can have some violations, and by observing that violations, it can eventually learn not to violate its constraint. But what we are trying to address in this part of our research is how to ensure constraint satisfaction throughout the learning, even in the first episode. And this is indeed a very important capability, because if you think about learning problems, the standard methods have asymptotic guarantees to learn the optimal policy. So eventually they will learn the policy, but we have to run the training for sufficiently long amount of time. But in reality, we have finite learning horizons. And in the case of finite learning horizons, again, the standard methods do not have formal guarantees. But with this constraint satisfaction during learning idea, if we can enforce the satisfaction of a desired specification even in the first episode, we can guarantee that a finite learning horizon may cause suboptimality, but never infeasibility. And another thing is that when we release these systems in real-world missions, the environment can change. So as they are learning something, they can adapt their policies. And if they have these constraint satisfactions, we can guarantee that while they satisfy their constraints, they can adapt their behavior. And this is also very important for long horizon missions, such as environmental monitoring, surveillance, or logistic tasks. So from a more mathematical perspective, in reinforcement learning problems, typically the agents are modeled as a Markov decision process. So it has the set of states, the set of actions, the probabilistic transition functions, and a reward function. And here you can see a pictorial representation of an MDP. And the classical reinforcement learning problem is learning a policy pi. Pi is a mapping from the state space to the action space. So mainly when I'm at a state, pi policy tells me which action I should take. So the goal is learning this pi policy that maximizes the expected sum of rewards. And in our research, as you see, we can again consider the same objective function, so learning a policy that maximizes the sum of expected rewards. But as a constraint, we can enforce that in each episode, we want a desired constraint phi to be satisfied with a probability greater than a desired threshold. So how do we ensure that in every episode of the learning? And in addition to that, we extend this idea, and instead of considering sum of reward form, maybe you can have a more complex objective like a capital phi specification. So can we learn a policy where the objective is not in the sum of rewards form, but in a more complex form. And at the same time, it has some constraint where you have this probabilistic constraint satisfaction. So here, I just want to show you a demonstration as a preliminary work from our paper. So here you will see a drone, and this drone, suppose that it's the pickup and delivery drone, and the pickup area is green, delivery area is blue. So we say that this drone has to achieve the pickup and delivery mission with a probability greater than 0.95 in every episode of the learning. So no matter what, we want to see this drone to go to green and blue. But as you know, these systems have cameras on board, and they can also be used for monitoring missions too. So let's say in the environment, we have some high reward zone, and we indicate it with this purple region. But in the beginning, drone does not know about this region. And let's say these areas are the no-fly zones. So here you just see some illustrations of the trajectories in the beginning of the learning, middle of the learning, and end of the learning. So it just explores the environment, the white area, but as you see, it just does the pickup and delivery by moving to green and the blue region. And after we wait for a while, it actually identifies this purple region. So it spends some time over there, but you see that it still continues exploration in the white region. But no matter what, again, it tends to go to green and blue region and continues its exploration. And after some time, it now understands that this purple region is the highest, the reward region. So it spends most of its time in the purple region and then quickly goes to the pickup and delivery locations. So this is the optimal behavior that we want to see in this problem, where pickup and delivery is the constraint to the system and learning the purple region is the objective. So this project is funded by DARPA, and we are investigating constraints in the learning problem and more sophisticated things in the learning problem. And if you have any questions, I would be happy to provide more details.
Thank you very much, Derya. All righty, next up we have Brad. I think you'll be able to share your screen and then continue when you're ready.
Great. Be happy to pull that up. Give me 1 second. Okay. Thanks, everybody. So I am an associate professor in the College of Design, which immediately makes me a little bit different than most of the other folks that are affiliated with the Robotics Institute, because I sit outside of College of Science and Engineering. There's good reason for that we don't have time to go into. My background is entirely in engineering, in aerospace engineering, to be particular, but I now sit in the College of Design, where I co-direct a research lab that focuses on wearable technology. And in addition to that, I am the director of a graduate program that focuses on human factors and ergonomics. So one of my particular areas of interest are wearable robotics, both the technology of wearable robotics, but also the user experience of wearable robotics. And I think Nikos gave a really great segue into this idea of human-robot interaction being a critical new domain for robotics in general. It doesn't get more interactive than a robot that literally is on your body. So much of what we do in our lab focuses on the design of wearable technologies and wearable robotic systems, but also considers what it means to be a person who has a robot on you. And so I'm in the College of Design because our lab has its origins in apparel design. So much of what we work on is this question of, can we design robotic systems on the body, but do it using best practices for clothing design, because it's silly to approach the problem of making wearable systems while ignoring, decades and centuries of work in textiles and soft goods manufacturing and patterning from 2D to 3D systems. So it actually makes a lot of sense for a wearable technology lab and, my subgroup, which looks at wearable robotics, having an apparel design centric methodology. And apparel design is a discipline in the College of Design, which is how I ended up there. So our lab really briefly blends this boundary between engineering and design, but also user experience. So we can look at technologies, we can look at manufacturing, and we can look at the engineering of systems on the body, while also thinking about humans as a participant or a collaborator with a robot that's right next to them and on them. So our lab, if you were to physically go in it, would look like a combination of an apparel studio and an engineering lab and a user testing facility. So you'll find, typical 3D printing and tensile testers and engineering equipment. You'll find sewing machines, you'll find pattern stitchers, and you'll find motion capture studios, among other things. And it allows us to do some, in my opinion, really fun stuff at this intersection of technology and human, with a robotics perspective. So to get into what I want to talk about today, we think about wearable robotics, but in particular, we look at soft robotic systems. So getting away from the paradigm of big, rigid, powerful, but bulky systems on the body, which are sort of the robots classically imagined, and exoskeletons being a prime example of that. They're big, they're powerful, but they are rigs, they're superstructures that sit on your body. What happens if robots now enter this space of soft robotics, which, as we all know, is an emerging discipline, but what if those are soft robots that are on our body? And can we get them to the point that they're indistinguishable from the clothes that we wear every day? And what does that mean, while providing some sort of robotic aspect of, control and actuation and sensing to a person without sacrificing the important things that we care about in the clothes on our body right now? So we study in our lab many different types of actuators that are soft in form factor, but still robotic in nature, meaning they have a actuation, a stimulus response behavior that can give us mechanical effects. If you want to define a robot, that's how I would define it. And so there's dozens of materials that are alternatives to your standard hydraulic or pneumatic or servo, electromechanical type of actuators that have a mechanical response behavior to it. And so we look at these exotic, oftentimes called artificial muscle materials, in particular for integration into wearable systems. And one of the materials that we work often with because of their commercial maturity are what are called shape memory alloys. So those of you that have some familiarity with shape memory alloys, typically you call them SMAs, they are temperature responsive materials. And over a certain range of critical temperatures, they will go from malleable and deformable into stiff and elastic. And you call that the shape memory effect, which means as you heat it up, it will change shape into a shape that we care about. And that you can engineer. And above those critical temperatures, the metal will act elastically. So you can call that a super elastic effect. So there's two really useful properties of these alloys, which is that as you heat them, they will conform and create a shape that you can engineer. And then above those temperatures, they will be elastic, so they can respond elastically on the body and be deformed and provide a force. So that's a really useful property. And we take these materials, which you can buy off the shelf, and we do a bunch of manipulations to them to make them useful for wearable robots. One example is taking these wires and forming them into very tightly wound millimeter diameter springs so that they achieve the behavior you see on the screen here, which is that when they're low temperature, you can deform them and extend to them. And when you heat them up, they recoil. So they shrink down to their shortest length. And in that form, they act as an artificial muscle and produce linear forces and displacements. So here's a video of one of these. Here we flip the switch, we have an actuation effect. One of those springs is about 1 millimeter in diameter. They run a bunch of them in parallel, and they become a really useful artificial muscle. So this whole structure on the slide is about 1 inch, maybe a bit more than 1 inch in length. And it's mostly soft, except for those end caps, which we 3D print. Now you can take a structure like this, place it at the seam of an otherwise passive garment, and produce a muscular effect. So a pulling force or a displacement or a tension or a pressure. We also work really closely in collaboration with another lab here at the U and with another faculty member, Professor Juliana Abel, who's in mechanical engineering and also part of the Robotics Institute, to look at creating textile-based actuators. So can we take these same shape memory materials and form textiles entirely out of these materials? And if you can do that, what are the actuation properties and what are the opportunities then to take these textile actuators and make useful systems on the body? And one of the strategies that has worked very well is to knit these materials. So this is an example of a metallic knit made from an SMA that, again, when heated up, creates a pulling force. And it's entirely textile based. So because this is a textile, it very easily integrates into a garment, but as you can see, can create actuation properties where one axis of the textile shrinks and the other axis of the textile expands. And every time that you heat it up, you'll see this similar behavior. So I don't have a lot of time left dedicated to me, but I'm going to go through a whirlwind of quick examples of how we use these systems to make useful wearable robots. And then we can talk about them in more detail when we have time for questions at the end. So one space where wearable actuation can make a big difference is in the medical devices space, in particular in the design of compression garments. Types of compression garments you see on the market right now are one of these two form factors. Either they're a big inflatable, which requires you to sit still while they compress you. The other is an elastic stocking that's too small for you, and which is a pain to put on and squeezes you all the time, even if you might not need it. Imagine now you make a garment that includes some of these shape change materials out of it, and now you can make a compression garment that can squeeze you strategically, dynamically, and change those locations and magnitudes over time to give you much more elaborate medical interventions for poor circulation. So we've had a project with the Mayo Clinic, now with the University of Minnesota Medical School, looking at these as deployable solutions. We also look at compression garments for behavioral intervention. So people use compression garments on the upper body to try to calm people down. If you've ever seen thunder shirts for dogs, or you've swaddled an infant, or you've worn a weighted blanket, there's a lot of evidence out there that haptic compression on the upper body can calm you down. But the same problems exist in the technologies on the market today for these types of interventions, is that either they're a big inflatable, or they're an undersized shirt that's just always squeezing you, or taken to the extreme, they're a crazy contraption like you see in the bottom right here, where you stick somebody in a giant roller device just to push against their body. We can make upper body garments that do the same thing, that include these actuators effectively hidden along the seams that can give you dynamic compression at the flip of a switch or by a press of a button on your phone. So here's a child-sized garment that can give you, again, dynamic squeeze. And we've been able to show you can squeeze people beyond the magnitude of a medical grade stocking unobtrusively, using these actuators, again, hidden down the seams of the garment. We can also produce these for adults. There's no reason that this can only be for children, even if we're targeting things like anxiety or autism or sensory processing disorder. Adults respond well to this stimulation as well. So here's a garment that, again, down the side seams, across the shoulder, even down the arms, you can create dynamic compression. We've also started studying these systems as interactive devices for virtual and augmented reality. So now having this ability as a platform across the body to squeeze people strategically to give them stimulation can create opportunities for novel experiences. So this is an example of one of these garments in action. The great thing about these actuators is each one is effectively just a resistor. So you can control them independently from one another. Here you see us toggling some of the channels across the shoulder and then strategically activating more and more and more of them to create dynamic effects, again, both spatially and temporally. This is all relatively easy to do with these types of actuators. We've also worked on exoskeletons themselves. This is an example of a 2-layer garment that's entirely soft. The lower layer includes textile-based stretch sensors. The outer layer includes shape memory artificial muscles running across the front of a shoulder. You could put this on a child that has a mobility disorder, and now this will give you both the ability to sense and support shoulder add and abduction. So again, exoskeletons reimagined without any rigid materials whatsoever. And then finally, I mentioned we work with these as knitted garments. This is an example of what a knitted textile looks like wrapped into a compression garment. So on the right, you see a heat gun applying some simple surface heat to this textile, and you see the panels of the material pulling closed. You now can wrap that around the leg. You can stage it at different densities, different ratios of active versus not active materials. And you can make some really elaborate robotic garments that are literally 100% textile based. And here's one final example of what a custom leg sleeve could look like that uses these knitted actuators. So if you know someone's shape of their leg, you now can create completely three-dimensional, completely conforming, topographically perfect garments to fit what's a pretty complex shape of somebody's lower leg, to give them, again, a custom experience and a custom fit that requires nothing more than the application of heat. So that's the end of my short talk here, but this scratches the surface of what we think about in the Wearable Technology Lab, which is this question of, can we blur the line between robot and clothing? And what are the technologies required to do that? What are the user experiences of wearing it? And what are the interesting ways that we can take advantage of that, so that the things that we wear can no longer be passive garments? They can be robots that we interact with and interface with throughout the day. So that's my pitch. I'll stick around for questions, but keep things moving. I'll hand it over to our next speaker.
Thank you so much, Catherine. If you want to share your screen, I believe you'll have the ability to do so.
All right, thank you. Can everyone see it?
Perfect.
Great. All right, let me start. Thanks for inviting me here. It was a great pleasure to be here and talk about our research. And I'm an associate professor at Computer Science and Engineering, and I will be talking mostly about our recent research attention in AI systems here. So very broadly, an overview of what our lab does. We primarily work on computer vision, machine learning, and some exciting applications, mostly with clinical and healthcare applications. So in computer vision, we perform some core vision tasks such as attention, detection, see understanding, as well as some emerging topics that across other sub areas of AI, like reasoning, language, and robotics. In machine learning, we tend to develop new methods that address primary challenges in vision and in healthcare domains. We focus on deep neural network lately. And we also develop innovative experimental methods and build high quality, large scale kind of data sets. So these integrate very well to address exciting topics, some of which are highly interdisciplinary, like computational mental health, like decoding neural signals to restore hands for amputee patients, and so on. So in the next about 10 minutes, I'll illustrate some of our works in attention and its integration to machines. So here I borrowed the working definition of attention from William James, the father of American psychology, who said more than 100 years ago that we all know what attention is. It's essentially the withdrawal from some things in order to deal effectively with others. And the input to our retina is simply much more than our brain can handle in real time. So we have to attend to somewhere in order to react in real time, and it has an evolutionary significance. The same thing for machines nowadays, with an overwhelming amount of sensory data. So knowing where to look at and making inferences accordingly is very much helpful for machines, for those autonomous agents to answer questions, to solve problems, and to navigate and interact with the world with greater autonomy. And it also causes all sorts of economic and maybe political interest for people who would like to control your eyeballs, influencing your reasoning and decision-making process. So this slide sketches the development of attention research. before the year of 2006, people predominantly use synthetic images and the traditional setup to collect data. The transition to more naturalistic scenarios was more recent. And I'll be introducing a few works that reflect our contributions to this transition that features naturalistic scenes, big data, and immersive paradigm. So we first addressed the so-called scalability challenge. This has been a long-lasting challenge in attention research that makes the study pretty small scale, as data collection depends on highly customized and most of the times expensive eye tracking devices. So I'm not going to the details, but we innovate an experimental method that allows the collection of high quality gaze data with general purpose devices like iPad, like general computer mice, and so on. So it collects 1.8 million trials. The data has been much larger, orders of magnitude larger than other eye tracking data sets. Since 2015, still the largest ones, and it's been very widely used in the community, both academia and industry. Companies, they use the data sets to develop products, for example, for compression, for redirecting user attention, and so on. So most state-of-the-art models in the research community has also been developed with this data set. We also hosted workshops and challenges to promote the use of big data in vision and related fields. Our online challenge site has attracted close to 1,000 submissions so far in the last few years. In parallel with the data effort, we've also been developing deep learning models that for the first time achieve human-like capability in finding important and relevant information to look at. We built an online demo site where you can go to the demo site, silicon.net/demo, and upload your own image to see how the demo predicts where you look at. So the distinction feature of this model is that it will highlight important semantics rather than the low-level features, textures, and so on. And it works pretty reliable for different types and different types of scenes and types of images, making it one of the most popularly used model in the last a few years. And then, after successes in predicting where people look at, we make a step further and try to integrate this attention capability into machines to support and then perform a variety of tasks. And here I will illustrate a task called VQA, visual question answering. So this is a task where machines need to answer open-ended questions when viewing an image or a video. So as you can see, this is probably not a trivial task for machines. It requires knowledge. It requires the capability to understand the process vision and language, right? So it's a task that machines haven't yet performed as well as tasks, for example, for recognition. And I also illustrated with this immersive paradigm, which mimics the embodied environment as humans or generally machines need to perform. So pushing this realistic concept here. And we build a diverse IQVA data set with diverse sources of immersive videos, questions and answers, as well as the correctness of answers. So this is the first time that we build a very principled data set that involves answer correctness. And comprehensive experiments then are enabled to identify the correlation of where people look at and the task performance, in this case, the answer correctness. And for example, we find that people who answered correctly usually attend to the important information relevant to the questions. And incorrect answers were a result of various reasons. In this case, it's because the answers are grounded in less salient regions. And remember, here in the immersive paradigm, information comes from all directions. So there's easily information overload, just as what we have in our daily lives. And secondly, we found that subjective bias may also lead to biased attention. So here, people answer car instead of truck in this case. They simply not look at the back of the vehicle. And thirdly, attention could be distracted by visually or semantically similar objects. So in this case, some people are distracted by the street lamp that were very similar to the flagpole as asked in the question. So they answer incorrectly. And finally, timing is also critical, just as in our real life situations. We have to look at the right place at the right time. So in this example, those who missed the train driver as it went by may fail to generate the right answer. And it shows that where we look at is contributing much to our task performance. And then we build deep neural network models that features attention and memory, as well as leveraging both types of attention, correct and incorrect attention, to perform a wide variety of tasks. So please note that incorrect attention, the regions where people would look at or models tend to look at, but are not relevant to the task, the distractors, they're widely ignored in the community. And we, for the first time, leverage this to build models, which demonstrated much enhanced performance in both attention prediction as well as the task at hand. In this case, the accuracy of answers when answering questions. And then the next step, besides demonstrating that attention is helpful for model performance, we further leverage it as an interface to visualize the decision-making process and try to improve that. So for example, deep learning models have achieved great performance gains, but we found that those models, they fail to look at where at least humans perceive as important in answering a question. For example, in order to answer this question, what is the man with the backpack holding here? Here are the regions where the deep learning models look at when we visualize them. And instead, answering the same question, a human would probably first look for and select the backpack, right? It asks, what is the man with the backpack holding? Want to first find the backpack, identify the man with the backpack, locate what the man was holding, and finally query the name of the object in order to answer the question, right? This is a sequential process that we would do to reason, attend, and in order to perform this task. So in some of our recent works, we try to kind of build into machines the same capability to sequentially look for, to reason in order to perform a task, rather than simply applying deep learning, to do the superficial matching in order to generate the answers or perform other tasks. So I'm not going to too much details. And here we build a first data set with those sequential attention and reasoning annotations, as well as task performance. And we also developed a unified framework as a metric to quantify how good attention reasoning is. So this framework allows us to principally answer a number of questions that the deep learning community is interested in, and to compare different networks and so on. And finally, it shows that the framework, the model that we developed, under this framework is able to perform better than their comparative models, but more importantly, is a much enhanced capability with attention and reasoning, which is broadly lacking in existing computer vision models. So here, something that I really want to emphasize, that the takeaway is really the highlight of the intermediate steps, right? Revealing the decision-making process and the correlation with task performance, allowing identification and visualization of critical factors for task performance. So this is very important for AI systems and models. So we further demonstrate that attention helps models to perform vision, language, emotional tasks, and it also shows that attention reduces the data and label for training, as well as alleviating adversarial examples. And besides attention, our lab also works on other exciting topics that includes reasoning with knowledge, vision with planning and action, explainable and trustworthy AI, as well as machine learning methods for clinical applications. And here are the students, collaborators, and funding agencies that make all these works possible. And I'll stop here. Thanks very much for your attention.
Thank you very much, Catherine. That was incredible. And thank you to all of our speakers. Again, if you have any questions, feel free to either drop them in chat or unmute yourself and you can ask away. I just had one thing for Dr. Holschuh. I remember you speaking a little bit more on spacesuits and compression-based spacesuits instead of sort of air pressurized-based spacesuits. And I found that super interesting. It's like my favorite fun tidbit to sort of mention anytime I see a spacewalk in a movie or something like that. Could you just describe that kind of research a little bit?
Yeah, we definitely didn't have time to get into it, but the origins of most of these soft robotic technologies that I was talking about are based in the aerospace world, as I alluded to. And so I got into wearable soft robotics through the lens of spacesuit design. And to put it quickly, the spacesuits that NASA has been sending to space, since the moon missions are inflated. They're gas bubbles that are shaped like a human. And you put someone in it because it replaces the atmosphere that you're missing in space. Now you need the atmosphere to breathe, but you also need pressure against the skin because we have surface pressure here. Atmospheric pressure at sea level is 14 psi. And you need to replicate at least part of that in space. So NASA, since the 70s, has wanted to replace these inflated garments with skin-tight garments because your body doesn't care how it gets that compression. It just needs to be compressed. And so if you put somebody in a skin-tight garment instead of the inflated garment, you can get the same life support features, but none of the mobility limitations. The inflated suits are stiff because they're inflated like balloons. And so, you get the life support that you need, but they're almost impossible to move around in. So there's been this dream forever to say, can we put them in a skin-tight suit that will keep them alive just as well, but be easier to move in? And those suits have a special name. They're called mechanical counterpressure suits, MCP suits. But they've never worked well enough to go to space because they need to be 10 times tighter than a medical grade compression stocking in order to be effective. So you think about the worst, tightest fitting garment that you might ever be asked to put on here on Earth, a medical compression stocking, and you multiply that by 10, and that's how tight this suit would have to be in order to function in space. So these soft robotic systems have their origin in being activators for compression garments, but not just a compression garment, the world's tightest, most uncomfortable compression garment, which is what this spacesuit would be. So that's how we started using these actuators, and now we use them to try and solve regular compression garment problems because it's a much easier problem to solve than the spacesuit problem. But I think what you were alluding to is now if you, whenever I watch a movie that has spacesuits in it, if you see them and they look very easy to move around in and perhaps look sort of floppy and that the fabric isn't under an extraordinary amount of tension, it's fake. Because spacesuits have to be either inflated or incredibly tight fitting in order to actually work when you're in space. And so that Hollywood movie magic, like The Martian, when he's walking around on Mars and has that cool looking orange suit that just kind of drapes over his body, he'd be dead if that was a real spacesuit. And so these actuators help get us closer to a world of spacesuits that look more like clothes instead of big inflated marshmallows. But we're not there yet.
I was going to say, I just saw Moonfall, which was not meant to be the most accurate, but that's exactly what I picked up on. They were doing a spacewalk and their hands were working like normal. And I thought immediately to your presentation, of course. Does anybody have any questions from the audience at all? I don't see any in chat. And if not, I think we could let everybody go. I'll just wait a second more just in case. Again, thank you to all our presenters. You can see all of their work. If you go to our website, I just posted it in chat, csu.umn.edu/MnRI. All of the presenters are available on our people page. You can see it links to their wider profiles. I'm sure we have websites on there. all of the web people at the college do a great job, me included. Those are all my people. So yeah, thank you very much for hanging with us this afternoon. And let any of us know if you have any more questions. So thank you so much. I'll let everybody go.
Thanks, everyone.
Thank you.
Thank you. Bye.
Bye.
Thank you.